You know, for most of human history, some things were just, well, they were considered unknowable, immeasurable. And right at the top of that list was the speed of light. In fact, it wasn't even really thought of as a speed. It was just a presence, a state of being, not a journey from one place to another. But as it turns out, humanity has this remarkable knack for measuring the impossible.
And this was the big question that started it all. When you open your eyes, does the light from a star billions of miles away reach you instantly? For some of the greatest minds in history, from Aristotle all the way to Descartes, the answer was a resounding yes. To them, light didn't travel, it just was, everywhere all at once.
And it makes sense, right? It's a totally intuitive idea. You flip a switch and boom, the whole room is bright. You can't perceive any delay. For thousands of years, this simple, common-sense observation was pretty much undisputed fact. Light had no speed.
And then, there's this. The modern, incredibly precise value for the speed of light. This number is so huge that a beam of light could circle the Earth more than 7 times in a single second. This isn't just fast, it's the fundamental speed limit of the entire universe. It's about as far from instantaneous as you can possibly get. So that's the real puzzle, isn't it? This is a detective story that stretches across centuries. It's full of brilliant ideas, failed experiments, clues found in the cosmos, and even gears spinning in the dark. This is the story of how we managed to clock the fastest thing there is. All right, so here's our roadmap for this journey. It actually starts with a few whispers back in ancient Greece, but the first real attempt to measure it came from Galileo in 1638. He stood on a hilltop with a lantern and an assistant on another hill. The plan was to time how long it took for the light to travel back and forth. But the experiment failed. The delay was just too short for human reflexes to catch. Still, this noble failure was crucial. It proved that if light did have a speed, it was unbelievably fast. The answer, it turned out, wasn't on Earth's hills. It was in the heavens.
So, if Galileo couldn't measure it on Earth, where did the first real breakthrough come from? Well, not from lanterns or mirrors. The first person to actually clock the speed of light used something way, way bigger. A planet and its moon, acting like a giant cosmic stopwatch. Okay, so picture this. It's 1676, and a Danish astronomer named Ole Rømer is meticulously tracking the eclipses of Jupiter's moons. His job was to create super-accurate timetables for sailors to use for navigation. He focused on the moon Io, which zips around Jupiter like clockwork every 42.5 hours. But he soon noticed this perfect clock wasn't keeping perfect time.
What Rømer found was a really weird pattern. When our planet, Earth, was moving away from Jupiter in its orbit, Io's eclipses seemed to happen later and later. But then, when Earth was on the other side of the Sun and moving toward Jupiter, the eclipses started to catch up, appearing earlier than expected. Now, Rømer knew Io wasn't just randomly speeding up and slowing down. So he thought, what if the signal, the light itself, was taking longer to get to us when we were farther away?
And this was his moment of genius. The problem wasn't with the celestial clock, it was with the signal. The light coming from Io simply had more ground to cover when Earth was on the far side of its orbit. The delay he was measuring was literally the time it took light to travel across the vast diameter of Earth's orbit.
Based on his observations, Rømer calculated it took light about 22 minutes to cross the full width of Earth's orbit. Now, the modern value is actually closer to 16.5 minutes, but he was in the right ballpark, and this was revolutionary. For the very first time, light had a number attached to it. It wasn't infinite, it was just really, really fast.
So, Rømer's discovery was huge. He proved light had a finite speed. But his number was only as good as the measurements of astronomical distances at the time, which weren't great. To really nail down the value, the next generation of scientists had to figure out a way to bring the experiment back down to Earth.
Fast forward almost 200 years. A French physicist named Hippolyte Fizeau decided he was going to crack this problem once and for all. No planets, no moons, just a beam of light, a distance he could actually measure, and a seriously clever machine.
His method was just brilliant. Okay, so he shot a beam of light through a gap in a rapidly spinning wheel, kind of like a gear. That pulse of light then traveled over 8 kilometers to a mirror and bounced straight back. Now here's the genius part. If he spun the wheel at just the right speed, the light returning from its long trip would get back just in time for the next tooth on the wheel to move into the way and block it. So by knowing the distance and the exact speed the wheel needed to spin to make the light disappear, Fizeau could calculate the travel time with incredible precision.
And his result? an astonishingly good 313,300 kilometers per second. That's only about 5% off the modern value we know today. This was the first ever mechanical measurement of the speed of light on Earth, and it proved Rømer's cosmic insight was spot on.
So far, this story has been all about clever experiments, physical measurements of a physical thing. But this is where the quest takes a sharp turn into the abstract world of pure theory, where the speed of light suddenly appeared not just as a number, but as a deep, fundamental truth about our universe.
Let's meet James Clerk Maxwell. In the 1860s, he wasn't trying to measure the speed of light at all. He was working on something totally different. He wanted to unite the forces of electricity and magnetism into one beautiful set of equations. And he nailed it. But buried inside his math, he found something completely unexpected. See, deep within his equations, there was this startling prediction. They showed that a changing electric field creates a magnetic field, which in turn creates an electric field, and so on. It was a self-sustaining wave that would travel through space, an electromagnetic wave. And when Maxwell calculated the speed of this theoretical wave, it came out to be almost exactly the same speed Fizeau had measured for light. The conclusion was just inescapable. Light is an electromagnetic wave.
Maxwell's work really cemented the speed of light as a fundamental constant of nature. But it was Albert Einstein who took that constant and used it to completely tear down and rebuild our entire understanding of reality itself. This one idea from Einstein's 1905 paper on special relativity is one of the most reality-bending concepts in all of science. I mean, think about it. Normally, if you're running towards a baseball someone threw, it seems to come at you faster, right? But Einstein said that if you race toward a beam of light, it doesn't. You will always measure its speed to be exactly the same unchangeable value, c.
That just feels impossible. But if the speed of light is absolute and never changes for anyone, then something else has to give. And that something else is space and time. To keep the speed of light constant, time itself has to slow down and distances have to shrink for people who are moving. The simple quest to measure a speed led to the shocking discovery that space and time are not fixed, they're flexible. So, we went from thinking light was instant, to measuring it with planets and spinning wheels, to realizing it's a fundamental constant that literally shapes the fabric of spacetime. But the story has one final, fascinating twist.
Let's just look at this number one last time. For centuries, this was the prize. This was the number that physicists were desperately trying to pin down with more and more accuracy.
Because here's the final twist. We stopped measuring it. In 1983, our measurements got so good, so consistent, that science decided to just flip the entire script. We fixed the value of c by definition. It's now an exact, unchanging number. And today, we use that constant to define everything else. A meter is now officially defined as the distance light travels in a tiny fraction of a second. The very thing we spent centuries trying to measure has now become our ultimate unchanging ruler.
And that brings us to one last really deep thought. Every single experiment we've talked about, from Rømer to Fizeau to our modern lasers, they all measure the average speed of light on a round trip, out to a mirror and back again. We've actually never directly measured its one-way speed. Why? Because to do that, you'd need two perfectly synchronized clocks far apart, but to synchronize them, you'd have to know the one-way speed of light in the first place. It's a classic catch-22. And it leaves us with a profound question. If we can't be sure that light travels at the same speed in all directions, how can we ever really know if two distant events truly happened at the same time? The quest to measure the universe's ultimate constant leaves us questioning the very nature of now.